Two pizza shops on the same street, same ovens, same dough, same delivery cars. Shop A get your pizza to the door in 8 minutes every time. But on the Friday night they top out at maybe 7 pizzas an hour. Shop B takes 22 minutes per pizza, sometimes 30. But on Friday night they push out 30 pizzas an hour, 4 times more. Same kitchen, same staff, same equipment. Why are these numbers so different? Because one shop is optimizing for latency and the other is optimizing for throughput. And here is the thing nobody tells you in their first system design course. The minute you start optimizing one, you usually start hurting the other. By the end of this video, you will know exactly what these two words mean, why they pull against each other, and how senior engineers actually decide which one to chase. Let's get into it. Two simple definition, memorize this. Latency is the time it takes for one request to complete, order to door, click to page load. You ask the system for something, you start a stopwatch and you stop the stopwatch when the answers come back. That's latency. We measure it in milliseconds or seconds. Throughput is how many requests the system can handle per unit of time. Pizzas per hour, requests per second, transactions per minute. You don't care about any one of them. You care about the total. Different questions, different stopwatches, different answers. Here's the way to feel the difference. Imagine you are at the airport. Latency is how long it takes you personally to get through the security. Throughput is how many people the entire security line processes per hour. The Transport Security Administration cares about throughput. You care about latency. You are not having the same conversation. Stick this in your brain forever. Latency is about you. Throughput is about everyone. They are not the same number. They are not telling you the same story. This one distinction quietly powers half of all system design decisions you will ever make. Let's go back to pizza shop because this is the analogy that will stick. You own a pizza shop. You have a big oven. You have two strategies. Strategy 1, latency mode. A customer walks in. You fire up the oven just for them. One pizza goes in. 8 minutes later, one pizza comes out. Hot, fast. The customer is delighted. Now the next customer walks in. You start over. New pizza. 8 minutes. The customer experience is amazing. The shop owner is going broke. You are using one oven to make 7 pizzas an hour. Strategy 2, throughput mode. A customer walks in, you smile and write their order on a ticket. You add it to the queue. You wait. Another customer comes in, another ticket. You wait. Once you have 12 orders, you pack the oven with 12 pizzas, slam the door and bake them all together. 22 minutes later, all 12 pizzas are done. Per pizza, it took longer. But the oven was full. The shop owner is happy. They are pushing 30 pizzas an hour. Notice what just happened. The first customer in the strategy 2 waited 22 minutes instead of 8. Their latency got worse, but the shop's throughput went from 7 to 30. Better for the shop, worse for the customer. This is the trade-off. Batching is great for throughput. Batching is terrible for latency. Dedicated, no-wait pipelines are great for latency. They are terrible for throughput. Same kitchen, opposite priorities. You usually cannot have both at the maximum. And by the way, this isn't just pizza. This is your database. This is your message queue. This is your machine learning model. The shape of the trade-off is the same everywhere. There are 3 reasons every engineer needs this trade-off in their head. Reason 1. Your users only feel one of the two. A user does not care that your backend handles 50,000 requests per second. They care that their button click took 4 seconds. Latency is the user-facing metrics. Throughput is the operator-facing metrics. If you confuse them, you will build a system that looks great on the dashboard and feels broken in the real life. Reason 2. Interviews ask about this constantly. Optimize this API, scale this service, make this faster. None of those questions are answerable until you ask faster for whom, per request or in aggregate. Until you pin that down, you are guessing. Reason 3. Most production incidents are a latency throughput mismatch. You scaled the service to handle more requests per second. Throughput went up, but somewhere a queue started feeling. Latency for individual users spiked. The dashboard says everything is fine. Your support inbox says everything is on fire. This is one of the most common pattern in real outages. You learn this trade-off once and you will see it everywhere. Here's where we are going. This is a curve. Every system has one, and understanding the shape of this curve is what separates a junior engineer from a senior one. On the bottom of the chart, throughput. How many requests per second your system is handling. On the side, latency. How long each request takes. Watch what happens as you push throughput up. In the green zone, throughput is low. Your server have a plenty of headroom. Each request gets its own CPU time almost instantly. Latency is flat and low. This is the comfortable zone. Your system feels fast. Now you push more traffic in. You hit the knee of the curve, around 70 to 80% of capacity. Something subtle changes. The CPUs are now busy enough that new requests have to wait, even if just for a few milliseconds, before they get served. Queues start forming, latency starts climbing, throughput is still going up, but each request is paying a little more in the wait time. Now you push harder. You enter the danger zone. The queue are feeling faster than the system can drain them. Latency doesn't just rise, it explodes. A request that took 50 milliseconds at moderate load now takes 5 seconds or 10, or it's timeout entirely. Throughput might actually drop here because the system is spending its CPU managing queues instead of doing real work. This is called queuing delay. It is the single biggest reason latency goes bad in distributed system. So here's the senior engineer move. You don't run your server at 100% throughput. You run them in the green zone, maybe 70% utilization. You keep headroom. You pay for the servers that aren't fully busy on purpose so that latency stays predictable. That feels wrong if you are optimizing the spreadsheet. It is exactly right if you are optimizing the user experience. I want to be honest with you about something most courses won't tell you. The good news, once you internalize this trade-off, almost every performance decisions get easier. Should we batch these database writes? Yes, if throughput matters more, and no, if any single user is waiting. Should we add a queue here? Yes, if we are protecting downstream system. No, if we promise the user a fast response. The bad news, there is no global right answer. Latency optimized system waste capacity. Throughput optimized system frustrate user. Every team has to pick which one matters more, and most team picks wrong on their first try. They optimize the metric the dashboard shows them instead of the metric the user feels. And here's the punchline. The two are not symmetric. You can usually buy a little more throughput by tolerating a little more latency, but you almost never get latency back once you have designed for throughput. Choose carefully. 4 questions you should be able to answer by this time now. Question 1. What is the difference between latency and throughput? Latency is the time for one request to finish. Throughput is the number of requests a system can finish per second. One is per user, the other is per system. Question 2. Can you increase throughput and latency at the same time? Up to the knee of the curve, yes. After the knee, no. Pushing throughput higher, start queuing requests, which makes individual latency worse. Question 3. Why do most production systems run at a 70% utilization, not 100? Because the last 30% of capacity buys you predictable low latency. The moment you go above the knee, queuing delays kicks in and the tail latency explodes. Question 4. Give me the real example of optimizing for throughput at the cost of latency. Database batch insert. Message queue consumers that pull many messages at once. Machine learning inference that batches prediction. All of these make individual requests slower on purpose, so the system as a whole moves more work. The last one alone will save you in interviews. Before you go, take 30 seconds to log this in your mind. Takeaway 1. Latency is one request, one stopwatch. Throughput is many requests, one rate. Different metrics, different audiences. Takeaway 2. Optimizing one usually hurts other. Batching helps throughput, hurt latency. Dedicated pipeline help latency, hurts throughput. Takeaway 3. Real system run below maximum throughput on purpose to keep latency predictable. Headroom is a feature, not a waste. In the next video, we will get into the cap theorem, the trade-off that defines every distributed database you have ever used. If this helped you, hit subscribe so you don't miss the next one. The full system design playlist is in the link below. See you in the next video.